Okay, good morning all. Let's see another method of finding out the Z transform today. I had introduced you to this method in the last session, but let's take this again in detail. Okay, the method that we already have seen for obtaining the inverse Z transform is partial fraction expansion method. Okay, now we shall see another method that is called as long division method or power series expansion method. Okay, now this is something that we all understand. Okay, this is the basic equation. Okay, in the basic equation we know that this is the zeroth. If you just expand this summation, okay, this is the zeroth sample of x of 0, and which is associated with z to the power 0. This is the n is equal to 1 sample. N equal to 1 sample associated with z inverse, the negative powers of z. Whereas if you come on to the left hand side, it is n equal to minus 1, n equal to minus 2, and all these negative n samples would be associated with positive powers of z. Understand? So when your sequence in time domain is negative time sequence, then you should be rather trying to find the positive powers of z, okay, so that you can find out the negative time sequence. If the time domain sequence is positive time sequence, then rather you should try having the negative powers of z, so that you can obtain or extract the positive time sequence from there. Okay, so this is the basic essence of this long division method. Fine. Now that is what is being told. Fine. Now see here. So if you have this, okay, in long division method you will get a quotient, okay, and that quotient would be x of z, and that x of z would be in this form. And once you have this form, seeing this, we should be able to extract this. Okay, seeing z to the power 0 is 1, right? So if you have 1 beside any sample, means that's zeroth sample. If you have positive power of z, that is z power 1, that means what is there beside that? That is n equal to minus 1 sample. If there is z to the power minus 1, then n equal to 1 sample is associated with it. Everybody understand? So this is what I should be rather trying to obtain. In the earlier methods, what was happening? Okay, in earlier method we used to do that by partial fraction expansion method. Okay, by partial fraction expansion we used to bring it to the standard form, then apply the inverse z transform. But here it is different. This is quite simple compared to that method. We shall see how it is simple. Now, using the long division method or power series expansion method, find the inverse Z transform. The following. The first problem under that is this. So they have given us this x of z, okay, and the region of convergence is z less than half. Magnitude z less than half. That means the region of convergence is within the circle with radius half. Now, the same problem we have solved by partial fraction expansion method also. Okay, but how to solve this by long division method is what we're going to see now. So very first thing that you should understand is seeing the ROC. ROC very clearly says it is within the circle. It is inside the circle with radius half. When we say region of convergence is inside the circle, okay, what we understand is when you apply inverse Z transform on this in the time domain, we have to have a negative time sequence. So when we have to have a negative time sequence, what powers of Z are associated? Negative powers of negative time sequence is left-sided sequence. With left-sided sequence, what is associated? See here, with left-sided sequence, what is associated? This is left-sided sequence. What is also which powers of Z are associated? The positive powers of Z are associated. So we are actually interested in obtaining the positive powers of Z because region of convergence is within the circle. Understand? So positive powers means in your quotient of this long division method, you need to have powers like this, the positive powers. Okay, so that is what we are seeing. So this is done by again dividing the numerator by the denominator. Fine. But one thing that you should observe here is, if you have to have the positive powers of z in the quotient, then how the denominator should be arranged here. Okay, the denominator should start from a constant. Okay, and then the first term in the given denominator should come in the last term. You can see that here it is 2z square minus 3z plus 1. But when we write there, okay, we start writing it as 1 minus 3z 2z square. Okay, so we have just flipped the given sequence there in the denominator. So if you have this sort of arrangement, then we can have positive powers of z, otherwise no. So in with the purpose of having the positive powers of z, it is written like this. And what is the idea here? Just go on cancelling this first term. What is this first term here? It is z. So z needs to be cancelled. That means what you need to multiply to this particular equation. This is the first term. 1 is there. So 1 into z would be z. Z would go off. And similarly, there are other two terms also along with 1. So they'll become minus 3z square plus 2z cube. Now z and z go off. Okay, you're left with plus 3z square minus 2z cube. Now there is 3z square. 3z square needs to be eliminated. So if 3z square needs to be eliminated, in this place I need 3z. How can I have this 3z square? So multiply this one with 3z square. Okay, so it would become 3z square, and this would be 9z cube plus 6z to the power 4. This is what it is. So this 3z square goes off. Fine. Then here, if you just see this, okay, what is there? 7z cube minus 6z4. Similarly, you have to eliminate 7z cube, means 7z cube will come. Okay, and 15z to the power 4 will come. Again, 1 into 15z to the power 4 will eliminate this. So similarly, we can have, we can just go on and on and on, but we cannot go to infinity. So we need to limit it to 3 terms or 4 terms. Here it is limited to 4 terms. Now, what this long division method tells you is, this long division method tells you very clearly that the quotient, this is called as the quotient of this long division method is actually x of z. Okay, so that is this. What is x of z? Okay, x of z is this in long division method. X of z was given to be some numerator and denominators equation, but here now it is being expressed as power series expansion. This is also called as power series expansion. The method is called long division method. Okay, the quotient of long division method. Now this is what the quotient of long division method is. Okay, now they have just written this 15z to the power 4 first. They have written, then they have written this, then they have written this, then they have written z. Okay, now what is the coefficient of z here? What is the coefficient of z? Is it x of minus 1 or is it x of 1? So how to understand that? Just go back, see here. What is the coefficient of z? Coefficient of z is x of minus 1. Coefficient of z to the power 1 is x of minus 1. Similarly, what is coefficient of z to the power 2? The coefficient of z to the power 2 is x of minus 2. So that is what you need to identify here. See here? So this is quotient of, see here, this 1 is x of minus 1. This 3 is what? X of minus 2. This 7 is x of minus 3. This 15 is x of minus 4, and dot 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 dot. It just goes on and on. So x of n can be extracted like this. Since is there a zeroth sample plus something is there, a constant is there? No, right? So zeroth sample is missing. But that sample we should show as 0 because I need to show this arrow. See, the zeroth sample is starting from here. So it's on to the left side. So this is n equal to minus 1 sample, minus 2 sample, minus 3 sample, and minus 4 sample. And how did we understand this? This is supposed to be left-sided sequence. We understood that this x of n has to be left-sided sequence because the region of convergence was given to be within the circle with radius half. Okay, and for this to be possible, your quotient should have the positive powers of z, because positive powers of z, if it is there, then only we can extract this negative time sequence or left-sided sequence. Everybody is okay with that? Let's see the same problem, but with the region of convergence outside the circle. Okay, it's outside the circle with radius 1. So the analysis is little different. Now what is the time domain signal if you apply inverse Z transform? The time domain signal is right-sided sequence, and right-sided sequence are associated with negative powers of Z. So in the quotient, we need to have negative powers of Z. Okay, so that is what is told here. So we need to look at negative powers of Z. So how to have these negative powers of Z? See, this 2z square minus 3z plus 1 you take as it is. Now the higher power of Z is taken first, whereas in the previous method, since we wanted the positive powers of Z, we started with 1 in this position. Get that? Only the positioning of this particular, the ordering of this particular denominator term is what is important here. Now this Z needs to be eliminated. Understand? This Z needs to be eliminated. If you have to eliminate this Z, what needs to be done with this? How can we make this Z? Okay, so how can I make half Z inverse? If I multiply half Z inverse to this term, it would become Z. So that is what we need to have here. Multiply this equation for half Z inverse, so that the first term would become Z. The second term anyways would become 3 by 2 plus half Z inverse. Okay, so what we do on this, the same would be done on this. So let's not bother what we get with this, but yes, what we should get with this term, we should get a Z. For that to happen, what we multiply, we multiply this particular term by half Z inverse. So if you do that by half Z inverse, this is the equation we get. Okay, so this Z and Z get off, so you'll multiply this equation by minus, so this become minus, so plus Z minus Z goes off, so this is plus 3 by 2, plus 3 by 2 is taken here, this is minus half Z inverse, that is taken here. Now 3 by 2 needs to be cancelled. So if this has to be 3 by 2, okay, how can I make this 3 by 2? How can I make this first term 3 by 2? How can I make this? So see here. So this Z square needs to be eliminated first. Z square needs to be eliminated. So for that you need to multiply Z to the power minus 2. Okay. Then this I want to be 3 by 2. So 3 by 2 means what I need to do, I need to have 3 by 4, because in the denominator I need 3 by uh, 4. 3 by, in the denominator I need 4 means, okay, so what do you need to do? See here, 3 by 2 is there, in the denominator 2 is there, it's 3 by 2. I want 3 by 2 from here. So what term you'll multiply with this? With this term you'll multiply 3 by 4, z to the power minus 2. So z to the power minus 2, z to the power 2 would go off, and what remains? 2 into 3 by 4 would give you 3 by 2. So what you multiply with this should give you this term, so that it will get cancelled. Okay, so cancel that, and what is left out next? 7 by 4 Z inverse. How to get rid of the 7 by 4 Z inverse? By multiplying this equation by 7 by 8 Z to the power minus 3. If you multiply Z to the power minus 3 to here, Z square, you will be left with Z to the power minus 1. Okay, what we need? Z by 4, right? So Z by 4 we need means, sorry, 7 by 4 we need means 7 by 8 you multiply to this. So it would become 7 by 4, as we have done here. Okay, so here we have stopped with 3 terms. You can go one more step further. Okay, 3 or 4 terms is sufficient. Now now again the quotient is, again these quotients are what? X of Z. Quotient of long division method is X of Z. Okay, so that is what we did. Now seeing this, can you tell me what is this half, what is this 3 by 4, what is this 7 by 8, what is also, which sample is also Z inverse? X of 1 sample, X of 2 sample, X of 3 sample, 0th sample is not there. So our X of n would look like, it would look like this. 0th sample is not there, so let's say that is 0 and give this mark to indicate that this is our 0th sample. So if this is our 0th sample, this is n equal to 1 sample, n equal to 2 sample, n equal to 3 sample, and it just goes on and on and on. You can write one more term, not a problem. But you need to end it. Don't go beyond 4 terms. Okay, end it at 3 or 4 terms. That's sufficient. So this is long division method. So I've just taken 2 examples with the same equation, but with the region of convergence differing. Once it is within the circle, once it is outside the circle. Within the circle means it is negative time sequence with positive powers. Outside the circle means it is positive time sequence with negative powers of it. So if you understand this long division method can be done easily. Now let's see the continuation. Now that is regarding the long division method. I wanted to give you another problem in the partial fraction method. I had left one problem wherein you have uh, repetitive roots. Yeah, see this root 1 is repeating twice. Okay, so this problem I had not done. You know this, but I just wanted to give you because I had not covered this till now. Okay, quite simple. Those who understand partial fraction method and those who understand how to expand this by partial fraction method, it's easy for you. So first what you would do, again, the rule in partial fraction method is this x of z needs to be divided by z. So z is available here. So how would x of z looks like? The x of z looks like this. X of z by z looks like this. Okay, now how can I expand this by partial fraction method? See, a by z minus 1 square, b by z minus 1 plus c by z minus half. So I've just taken this out of the textbook. This is the method which they have used to find out ABC. Understand, there is repetitive root. Okay, because of this repetitive root, one is repeating twice. Okay, so because of this repetitive roots, okay, our expansion should look like this, which I think you're aware of. Okay, so this is the method they have followed in textbook. I've just copied and pasted that here. So you can go with any method, but see you obtain your ABC properly, and they are obtained to be 4, okay, minus 6 and 6. So substituting these ABCs in this equation, you'll get your x of z by z to be this, and once we take this z onto the right hand side, you will have this. Fine. Now there is a square term in the denominator, which is something that is rare in the examples that we have seen so far. So what is the inverse z transform of this? What is inverse z transpose z by z minus 1? Inverse z transpose z by z minus 1 is u of n, provided the region of convergence is outside the circle. What is the region of convergence? Let's see. The region of convergence is outside the circle with radius 1. So since it is outside the circle with radius 1, okay, with all the three terms, since it is outside the circle with radius 1, okay, with all the circle, with all the terms, we associated positive time sequence. Okay, so it is for z by z minus 1, it is u of n. For z by z minus half, it is half power n u of n. But what is it for z by z minus 1 square? Yeah, if you anybody remember that, what needs to be there is this. So applying the inverse z transform on this, we will avail this. So what is here? So if there is a square term to z minus 1 here, you need to associate this n. So it is n u of n. 4 times this z by z minus 1 square is n u of n. Understand that? Okay, this is u of 6 minus 6 u of n plus 6 half power n u of n. So I just took this example because there is repetitive root, and if you know what to how to expand this in partial expansion method and how to find these constants, you are through. So I just covered this example because I had not taken this before. Fine. Now let's go on with the last bit of this particular chapter, that is transfer function. Okay, you're all studying control system subject. Okay, in that control system course, okay, you know there is something called as transfer function. What is transfer function? Transfer function is represented by h of z in z domain. It is the ratio of output by input, y of z by x of z. So that you understand. Okay, in control systems, that is something that you've learned. Fine. So we have problems on that also. How to understand it? So you have a system, and every system is characterized by its impulse response, that is denoted by h of n. Okay, every system is identified by its impulse response, and that impulse response is represented by h of n. X of n is the input and y of n is the output. Now given x of n and h of n, the input and the impulse response, what would be the output of the system? The output of the system would be this h of n, and the star here is convolution operator x of n. H of n convolution X of n is the output of the system. Okay, so this is in time domain. The convolution is in time domain. Now, when would this convolution become multiplication? When would this convolution operator become multiplication? When you take this equation into Z domain, this convolution operator would become multiplication operator. So applying the Z transform implies y of Z. See, Z transform, this is y of Z. Z transform, this is h of Z. This operator convolution would become multiplication in Z domain, and x of n, Z transform x of n is x of Z. So when we have this, what is transfer function? Then transfer function is h of z equal to the output by input in z domain. Output by input in z domain is called transfer function, or it is also called as system function. System function or transfer function. Everybody understand that? Now we have problems on this. Okay, how to solve those problems we shall see. Just two problems I've taken. If you just understand that, it is sufficient. Okay, so it is there in your syllabus, the last bit of your syllabus in Z transform is this. Okay, let's cover that. Now see this, what is being told. Consider the system shown in the figure. Find the system function h of z. See, they say it is system function. System function means you should not uh, uh, mistake. Okay, it is transfer function only. Okay, which is h of z, and the impulse response h of n. How the h of n and h of z are related? Impulse response is in time domain. Okay, the z transform of this impulse response is system function in z domain, that is h of z. Fine. Now the system is given to be this. The system is given to be this. Okay. How to read this system? So this is the output. Y of n is the output. X of n is the input. So can I express the output y of n seeing this block diagram of the system that they've given? Okay. Now y of n is here. Okay. So how can I express this y of n? Okay, seeing this block diagram, that is what we need to do now. Now what operator is this? This is summation operator. Now there is an x of n coming. Okay, so this x of n is positive, so whatever comes here, this is plus x of n is what you need to take. Then whatever comes in this path, this is called as the feedback path. A part of y of n is being fed back to the input, and when it comes to the input, it gets added with the input because we have summation here. So it is x of n plus what is coming here. What is coming here? See, this y of n is tapped here. This y of n is being fed back, and it is being fed back through a block which is z inverse. So what does this block z inverse does? What is this z inverse doing? Z inverse, okay, shifts this y of n to the right by one position. Z inverse shifts y of n to the right by one position. And what is this? This is a scalar which needs to be associated with the term here. What is there? What is there here? Here is y of n. Here is y of n minus one. Okay. And what is there here? Here there is half y of n minus one, because this half is the scalar that needs to be multiplied to the signal here. So that's why. How would this y of n looks like now? That y of n looks like this. This is x of n plus this plus, okay, half y of n minus 1. Understand this? Now, by seeing this particular equation, can we say what type of system is this? Is it a causal system or non-causal system? Is it possible to say by seeing this? How can we say whether it is causal system or non-causal system? What are causal systems? Causal systems are the systems wherein the output depends on the present value of inputs or on past value of the inputs. It should not depend on the future value of the input. Here, it is depending on present value of input. This is not value of input, so this is depending on present value of input. Since this is depending on present value of input, this particular system is a causal system. So let's keep that in mind. So this is a causal system. Understand that. Now, what is asked? What is asked? We are asked to find out h of z. So if I want h of z, I want y of z by x of z. How can I obtain y of z by x of z? That I can obtain by applying z transform on this. What happens if I apply z transform? See here. This y of n would become y of z. Okay. X of n would become x of z by applying z transform. And this is something important. Why this y of n minus 1 is written as z inverse y of z? So by what property y of n minus 1 can be written as this in z domain? It is by time shift property. Since there is a minus 1 here, you need to associate z inverse term to the z transform of y of n, that is y of z. So this is time shift property. By time shift property, this is true. So those who don't understand, you can go look into time shift property. Okay, you should be aware of this particular thing by now, because you have read properties. Okay, you have written test also on that. Fine. So from this, give me the term y of z divided by x of z, so that I get h of z. So I get my h of z by getting y of z by x of z as this. So this is the transfer function. Okay, since this is z inverse term, okay, this is z inverse term, get it as z, express this in terms of z. I don't want this expression to be in terms of z inverse. Okay, so how to do that? Just express this as 1 by z, take the LCM and arrange it in terms of z like this. Now this is your h of z. Now what is, can I obtain h of n from this? Can obtain impulse response from this? How to obtain impulse response h of n? So impulse response h of n can be obtained by applying inverse z transform on this. Here, since the system is causal, okay, the region of convergence is outside half. The system is causal, the region of convergence is outside half. Okay, this was not given, but we should understand that the region of convergence, so the system is causal. How to understand the system is causal? By looking into the equation of the system. The equation of the system very clearly says that the output of the system depends on only the present value of the input, so the system is causal. Okay, that's why since it is a causal system, the region of convergence is outside the circle with radius half. That is what they've written here. Now what would the inverse z transform give us? So the inverse z terms of h of z is h of n. Okay, and what is the inverse z transform of this? The positive time sequence, it is half power n u of n, and this is your impulse response. We had transfer function here. The inverse z transform of transfer function would give us the impulse response, which is this. Everybody understand? Okay, let's fast take another problem and let's end there. See, yeah, very similar problem, very similar problem. In the previous problem, the system was given. Seeing the system, we obtained an equation that is called as difference equation. N minus 1 term is there, right? So that can be called as difference equation also. That is a system equation. From that, we obtained transfer function. Then applying the inverse Z transform, we obtained impulse response. So that is what we'll be doing here again. The output of the discrete time LTI system. LTI system means the system that we discussed. They're all linear time invariant systems. Okay. The output of linear time invariant systems are the convolution of the input signal along with the impulse response h of n. Okay. So discrete time LTI system is found to be y of n. That is this. Y of n is given to be this, and x of n is given to be this. The input is u of n. The output is this. Find the impulse response. How to find the impulse response when they have given us what? When they have given us the input and output. How can I do that? So to understand this problem, you should understand this figure. They have given us the output. They have given us the input. How to obtain the impulse response? How to obtain the impulse response? Impulse response is here somewhere. Okay, y of n is given, h of n is not given, x of n is given. Okay, but we know y of n is h of n convolution x of n. Okay, so what we can do, we can apply inverse z transform. You obtain h of z, apply inverse z transform of that, you will get h of n. So this is what is the thing that you need to follow. H of n is not given, we need to find out this h of n. But how to find out this h of n? Okay, by applying inverse z transform on h of z. So that is what we'll be doing here in the second problem. Okay, so let's take this. What is given? Y of n, the output is given to be 2 into 1 by 3 times n u of n. Okay, what is the z transform of this? So positive time sequence is there, right? What is the z transform of this? This is 2 into z by z minus 1 by 3 with region of convergence outside the circle with radius 1 by 3. Why it is outside the circle with radius 1 by 3? Because it is positive time sequence. Similarly, you take the input. You take the input. What is the input? Input is u of n. So you obtain x of z from that. Okay. So what is x of z? X of z is z by z minus 1 because it is u of n, positive time sequence. So it is outside the circle with radius 1. So they had given us y of n and x of n. Okay. Obtain y of z and x of z like this. And uh, what is the ratio y of z divided by x of z? That would give us h of z, that is transfer function. Now how to obtain the impulse response from this? How to obtain the impulse response? It can be obtained by applying the inverse z transform. But how to obtain the inverse, z transform of this? By partial fraction expansion. How to expand this partially? By partial fraction expansion. This is h of z. I need z in the denominator. Okay, since there is no, I cannot bring any this z onto the left hand side. What we did, we multiplied z to the denominator on both sides, so it looks like this. Expand it by partial fraction method and find out the constant. That would happen to be 6 and minus 4. Okay, so h of z by z would look like this. So h of z by taking the z on the right hand side would become this. The z and z gets cancelled, so we'll be left with 6. Okay, and here you have 4 into z by z minus 3, z minus 1 by 3 with region of convergence just z greater than 1 by 3. Since this region of convergence is outside the circle with radius 1 by 3, what would be the inverse Z transform? Looks like this. So we are asked to obtain the impulse response. So how to obtain impulse response given the transfer function? By applying the inverse Z transform. So apply the inverse Z transform on this. So there is one here beyond beside 6. So inverse Z transform of 1 is delta of n, that is that here. And z by z minus 1 by 3 will have a sequence 1 by 3 to the power n u of n in time domain. This is what is your impulse response. Understand that? Okay. So we have another question here which you would attempt yourself. I've not attempted this question B. Find out output when x of n is 1 by 2 power n. The hint is a system can have the same impulse response which we have found out in the previous system. They have given us x of n. We have found out h of n in the previous step. Okay, find out the output. So this is something that you can try yourself. That I have not done. I've left that for you. Okay, so here we shall end the Z transform. Understand that? Okay. So now you can start giving your attendance.